Welcome back to CS 520. Today I'm going to talk about maTe program representation. So maTe is a toy language with a toy virtual machine that was created here by a UNH student, partly for teaching purposes, but also it's been the basis of his master's thesis research as well. maTe is a pure object-oriented language, which means that everything is an object. This is in contrast to Java, which is not pure, since it mixes primitive types like int and float with reference types like with objects. Having a pure object-oriented language allows for a VM with a small number of instructions, because we don't need to have instructions to operate on the primitive types. Basically, nearly all operations become method calls. maTe has 4 native classes. Object, which like Java is the root of the class hierarchy. Everything grows from that. Everything is derived from that. And then there's 3 other native or built-in classes, one to represent strings, one to represent integers, and one to do hash tables. maTe is, again, a very small, strange sort of language. It doesn't have arrays, so hash tables are used to implement arrays, among other things. And why would we call these native classes? Well, again, they're the building blocks so that users can have something to build their user classes out of. And they're native in the sense that they're implemented natively, which means the methods for these classes are implemented with native code. In our case, that's C code that is compiled to the Intel. So again, these classes are where a user starts, right? A user can derive classes from these. The user methods then, the methods for the user classes will be implemented with the virtual machine instructions. Okay, so how do we translate and execute maTe programs? Well, it's similar in spirit to what you've done with Java programs. Again, there's a source code. maTe only supports single file programs, so all your classes have to be in one file. We take that file, we run it through the maTe compiler known as MC. Again, the student wrote this compiler, and that produces an assembly language. This is what is a little bit unusual from your Java experience, because Java hides this step from you. You don't see it. But in our world, we explicitly created an assembly language file, and then we have an assembler to translate that human readable assembly language code into a binary class file. Again, a class file is similar in spirit to a Java class file. The assembler it's a pretty simple program. That's why a 520 student could think about writing it. It just translates this human readable form into a binary form. Once you have the class file, then you feed that into the virtual machine implementation, which we call the maTe virtual machine, or MVM. And as I said a moment ago, a chunk of the code that's inside the virtual machine is this native code for implementing the 4 built-in classes. Okay, and again, MVM is simple enough that students, 520 students, could think about implementing it as well. So let's look at a maTe source code program. Here's everyone's favorite program that just simply computes 42. maTe is a little different than Java in that it has a main block where execution begins that's outside of any class. So all execution starts in this main block. In this case, we just output 42 and a new line on the end of that, and that's it. Again, this is a very simple program. Other maTe programs, of course, could have user-defined classes and methods and everything else. to take a look at other examples of maTe programs, take a look at the maTe tutorial, which is available from the website. For the hardcore, you can also take a look at the maTe programming language specification, which defines all the ins and outs of maTe. It's really meant for a compiler writer, though, but it does have all the details. Okay, so the maTe compiler would then translate that high-level maTe source code into assembly language. And it's this level that we're interested in this class. Again, this is a human readable form because it's assembly language of the class file. The assembler, though, translates this pretty straightforwardly into the class file. So this is really a human readable form of the class file. Let's take a quick look. The structure is actually fairly simple. Up here at the top is a description of where the main block is and actually how many local variables it needs. I'm getting ahead of myself a little bit, though. Again, I apologize, this print may be a little small. You want to pick up these slides. If you don't have them already, stop the video, pick up the slides from the website so you can look at the slides too and maybe take notes on them. First thing on this in this assembly language file is a comment, so these pound sign lines are comments. Then we see a reference to this label. So in maTe assembler, references to labels always start with a $sign. And somewhere way down below, we're going to see that label main block appear. It's actually right here. Label definitions, like in most assembly languages, are indicated by a colon after them. So there's a $sign at the beginning for a reference and a colon afterwards for the definition. And what this is telling us, it's telling us where the main block code is actually. It's way down here later in the class file. And in fact, you can see some more comments, but also some maTe instructions. These are actually instructions that are executed by the virtual machine. maTe is vaguely based upon Java, so these are close, similar to Java instructions in many cases. The next thing in the class file is the class table, actually. This is the critical feature that allows us to implement object-oriented languages, is the class table. So we look into this, and the first number here just tells us how many classes were defined by this maTe program. In this case, it's 4 because I don't have any user classes. I just have the 4 built-in or native classes. And again, there's 4 entries here to tell you where you can find more information about the class. Again, these are forward references. This is a reference to a label object. We can see it right here where there's detail about the class available, or for integer it's down here, and string and table and so on. So there's a little table here that has the address of where there's more information about the class, and then also the name of the class. Let's take a look at the detail for a particular class. We look at object. The first thing in the information for the class is an indication of its superclass. But because object has no superclass, again, it's the root of the derivation hierarchy, the class hierarchy, there's a 0 to indicate that that's the case. It has no superclass. If you look at integer, though, you'll see object is the superclass. The second item in the data for a class is the number of fields. Object has no fields, so it's 0. In fact, all the native classes have 0 fields. But a user-defined class that defines fields, that count would be kept in that second slot in the class descriptor. Then the rest of the descriptor is the number of methods and information about the methods. So there's 3 methods for object, and for each method there's this triple. The first one is where the code is located. Second one is the number of local slots that method needs. I better go check that. Again, all this information, all this detailed information is in a document called the maTe class file. And I can go look here just to make sure I've got this right. Right here's the method table. Begins with a word containing the number of methods. described by the table. Method table then consists of a list of triples with one triple for each method. The first item is the address of the code. Second item is the number of locals. And the third item is a string containing what's known as the munge name of the method. System, for its own internal reasons, creates unique names for every method, and the munge name is simply made up of the the class name, the method name, and then the types of the objects, with each component being separated by $sign. So okay. Now, these methods, though, are all special because they're in the native classes. So in fact, what's in the triple is 0, which indicates they're implemented natively. Rather than having a pointer to the code down below, we just have a 0 that tells us it's native. It's implemented natively. And the second column then is the what we call the native method index. It allows us to it allows the virtual machine to find the C code that implements that method. But normal methods for user classes would have an address of where the maTe instructions are to implement the method, and this middle slot would be the number of locals that method uses. Okay, so I can't resist talking a little bit about the structure of the class table here. Again, this is the secret to how object-oriented languages work. If you go back and look at the maTe documents, you'll see that object has 3 methods. Of course, we can see them here, and then those methods will be inherited, right, by every class that's derived from it. So we'll see here in the integer class we also have an equals method, a hash code method, and a toString method. But we notice that they've been overridden, right? The integer class defined its own version of these 3 methods. And that's the trick. That's how object-orientedness works, that I can create an integer object, and then I can manipulate it by a reference to an object rather than a reference to an integer, and the implementation simply uses an index into the class table to find the right method. And the maTe compiler arranges for the equals method to always be the first thing in the class table. We come down here and we'll see string overloads equals as well. But strangely, perhaps to your mind, you come down here and you'll see that table does not have a local overloading, so it uses the original equals method provided for object. Okay. And again, we see that method has the same name and the same native method index as we see up here for object. So again, the tricky thing here is we can create an object of type string, for instance. We can put the reference to that object into a reference of type object, and when we call the equals method of object, what we're actually going to get is the overridden method, because the object will have its runtime class information attached to it, as we'll see when we talk about implementing the VM in another lecture. And you'll end up invoking the first method in the class table for the class attached to the object, and that means you're going to get the equals method for string, even though in the program you may be thinking of the object as being just an object. So I probably shouldn't have talked about that right now, but I couldn't resist. That's what's going on here. This table layout is the key to how object-oriented languages work. So that's the class table. If we take this and we look down here, this is all information about the classes that are defined by the program, and in this case it's just the native classes, but if there was user classes, they would be tacked on the end here. There'd be an entry up here, and then there would be additional descriptors down below. But after the class table, all that we have left is the code. So the rest of the file, again, this is the class table, and then this is the code. So this is the instructions generated by the compiler to implement, in this case, just the main block. But if there was user classes with methods, there would also be the instructions to implement those methods. So if we look again, just quickly go back and look at the original program. The original program was just outing 42 and then outing a new line. How does that? What does the compiler translate that into? Well, it creates an integer 42. So there's actually a virtual machine instruction to create an integer value, and then it does an invoke virtual of method number 2. And what is the number 1? Well, we can look that up. Let's take a look at that. I'm sort of getting out of order. I got off my script. Let's just peek ahead, though. What is that virtual machine instruction going to do? Well, it's called invoke virtual. It takes an index and a number. So index must be the index into the method table, the class of the object, and then at the end is the number of arguments that are going to be passed to that method. Okay. So in this case, we're invoking method number 2. It's being applied because this is a stack-based machine, just like Java. It's being applied to the item on top of the stack. So each instruction, this instruction is producing an integer value. It's placing it on top of the runtime stack, and then we're invoking a method on that object. So it's an object of type integer, and it's going to use the second method in the class table for integers. So we go up here and they start with 0, 0, 1, 2. So that means that instruction actually is going to invoke the toString method, which is the overriding of the toString method that was inherited from object. And that method needs one parameter, which is just the reference to the integer object itself. So we're converting the integer 42 to a string, so it's going to pop off 42 from the stack, top of the stack, and it's going to convert it to a string, placing a reference to the string on top of the stack, and then finally it's going to output that string. Okay. And a similar thing, although simpler, happens for the new line. It creates a new line. So it's a new string, similar to new int, except now we're creating a string object that contains the string, which is just a new line. Again, this assembly language is a little bit unusual in that the new line actually just gets represented by a new line here. So that's why you see it's skipping down to another line. And then we output that. And then the program exits returning a 0, which is the default return value. Okay. All right. I'm supposed to just be talking about how programs are represented, so I keep getting off track here. Let's take a look now. What happens after that's assembled? The assembler is basically outputting the assembly language as a series of 32-bit integers. So if we look in here, the comments will be thrown away, but the address of the main block will be put into a 32-bit integer. I believe it uses big endian format for these integers, these 32-bit integers. And the value 0, which is the number of local slots the main block uses, is put in another integer, and the value 4 is put into an integer. So it's just encoding all these things as 32-bit integers. Now, even the strings, so the designer of maTe didn't care about space efficiency, because even strings, each individual character is put in a 32-bit integer. So if you look at the output of the assembler, again, let's go back and take a quick look at the tool chain here. How does this work again? On an earlier slide, we were looking at this, right? take a source code program, we compile it, we're looking at the assembly language code. Assembly language code is then run through the assembler to get a class file. And what does this class file look like? Again, it's a binary file, so we need to look at it with OD. So if we look at the class file for this program that prints 42, we're going to see this. Again, you'll probably want to get these slides so you can take a look at them in case this print is a little fine on the screen. But it starts out with, it's a series of 32-bit integers. I've just done TX1 here on OD, so it's just showing me the bytes in order in hex. And it starts out with that number. Well, that number is in fact where the main block code is located, down below. And what is an address in this machine? The tricky thing here is that class file is a sequence of 32-bit integers. But an address is a byte offset. It's a byte offset in the class file. So this address here, which corresponds to that $main block in the original assembly language, is the byte offset into this class file where we would find the code for the main block instructions. Okay. Let's just do a couple more words in here. We do the second word. This is the 0. So this corresponds to that 0 there. Again, that's how many local slots are needed by the main block. The next field is the number of classes in the file. And again, we see that right here, 0004. And again, you can see with these integer values, especially with this 4 one, I guess you can see that it's in big Indian format, right? The big byte came first. The low byte came last. Okay. Then the 8C is where there's more information about the class object. That's the reference to this $sign object. Again, it's a little confusing because OD is showing us this in octal, and that's obviously in hex. But basically, all these things are encoded in a 32-bit integer, including these strings. Maybe we should take a look at that. Let's take a look at that next part, because we have, after the $sign object, which is going to be this 8C, then we see these fields. (4F, 6.2, 6A). So, one. Right. My theory is that's O, B, J, E, C, T, E, C, T, and then there's a null on the end. Okay, so it's strange, right? Each character is packed in a 32-bit integer. Okay, you can check those ASCII codes, but I think that's what's going on there. Okay, what I want to skip to though is I want to skip down and look at how instructions actually are represented. The class table again is fairly straightforward once you understand the trickiness about these strings, that they're represented each character in a 32-bit integer. But you know, these addresses are just 32-bit integers, and these integer numbers are just 32-bit integers. So the rest of this encoding is pretty straightforward. But let's go down and look at the code itself. How are instructions actually represented? And we go down here again. These are comments. We see these instructions. Well, let's try to find that code in the OD dump. Again, I go back here and I pull out this address at the very first word. It's ED8, which obviously is base 16. I need to convert that to octal for my octal dump. And I think if I do that, I end up with 7330 in base 8. Okay, again, I'm just taking that first word. It tells me where the main block code is. I'm taking the hex, translating it to octal. And now I can go look through the reams of OD output that I have here and try to find where that is. And it's way down here. Okay, here I'm looking for 7330 in octal. Here's 7320. So that means, and again, these are byte offsets. Remember, these addresses are byte offsets. Very confusing, actually. But 30 in octal is 8 bytes over. So we skip over 4, we skip over 8. So in fact, the code starts right here with that F7. And in fact, the instruction, the first instruction in the main block was new int 42. Let me just go back and make sure that's the case, right? If you go down here and look, there it is, new int 42. That's the human readable form. If we look at it in hex, it looks like it's represented as F7, again as a 32-bit value. So let me just write it out that way. F7 followed by 00000002A. Well, what's the F7? Well, the F7 is the encoding of that opcode, we call it. Right, each instruction has an opcode. Again, we took a look at this with VM 520, I guess. So we can look up new int in what? You can look up new int in another document available, which is the maTe virtual machine instructions, which is the specific details of each instruction. We look through that manual, we can find new int. Okay, and it tells us that new int takes two words. It takes two 32-bit words. One is the encoding of the opcode new int, and it tells us that the encoding in fact is F7, and that the second word will contain the value that is to be placed into the new integer. Okay, so these descriptions talk about exactly what the instruction does as well as how it's represented. So again, this is a stack-based machine like Java, so what it does is it takes a stack, it doesn't pop anything on it, rather it pushes the new object reference for the new integer object on top of the stack. That's what this notation is telling us. And then there's an English description down below. The key thing for right now, though, is that it's encoded as F7, which is what we expected. we see the F7, and then the 2A is the 42, right? 2, this is hex now. 2 times 16 is 32, plus A is 10 is 42. So that's how this instruction is encoded. We jump around, then the next word is going to be in the code is B6, which is supposed to be invoke virtual. So the next thing we see in the program is invoke virtual. Excuse me, 2 and 1. Okay, so the B6 must be the encoding for invoke virtual. If we go and look, sure enough, invoke virtual, it takes 3 words to represent the instruction: the opcode, the method index, and the number of parameters that are being pushed. It describes how the instruction is encoded, that the opcode is B6. It describes the impact on the stack. It takes an object reference and additional arguments. This object reference counts in the total count of the arguments here. And then a long English description of exactly what's going on. It has to do with the passing of the objects and the calling of the method and so forth. Creation of frames. Okay. So sure enough, we see the B6, and then of course we see the 2 and the 1. Okay, so it's a pretty straightforward encoding of the instructions with 32 bits for every component. All right. So that in a nutshell describes the class file and how it's represented. What we'll do next time is we'll think a little bit about how would you operate to read in that class file, because if you think back to the tool chain again that's used to translate and execute maTe programs, again there's a compiler, there's assembler, but then the last step is the virtual machine has to read in that class file before it executes it. So what we'll talk about next time is what does it take to read in that class file. So let's stop here.